Hello everyone, my name is Avkash, and in this exercise you are going to learn generating a sequence of numbers based on a given input sequence. Your input sequence can be any mathematical function. It could be a quadratic equation, it could be the exponential or the logarithmic function, or it can be either a trigonometric functions started using sine, cos or tan. This exercise is divided into two separate exercises. The first exercise is going to help you to learn how to generate a number series based on a given mathematical function. And in this section, we are going to use the NumPy and Pandas. And you are going to generate the sequence of x and y, where x is a sequence of number and the y is a function which is dependent on x. In the second part of our exercise, we are going to use any of the sequences which we have generated in the first part of this exercise, and using Scikit-learn regression method to build our machine learning model. That model learn the sequence from the given input series, and using machine learning model we are going to generate n new numbers. Once our predicted sequence is generated, by combining the predicted values as well as the source values, we plot the graph to validate and make sure that the sequence generated by our Scikit-learn regression model is correct and these new numbers do lie in the same pattern as the source sequence. In this tutorial, we are going to cover Pandas, NumPy, Scikit-learn and Matplotlib library to achieve our objective. So let's get ourselves started. So this exercise is divided into two exercises. In the first exercise, we will learn how to generate various number series by using mathematical functions. These functions are quadratic, exponential, logarithmic, and sine, cos, and tan trigonometric functions. And this Jupyter notebook is going to help you to generate the numbers depending on whatever mathematical functions you are going to use, and you can generate your number series by using a noise and the non-noisy functions. So here is the series which does not have the noise, and here is a series which has the noise, and by using a plotting function to see these numbers side by side, sequence without noise and sequence with noise by using various mathematical functions. So we are going to use various quadratic function, as well as we are going to use exponential function, the logarithmic function, and the sine, cos, and the tan function. You are going to learn so many creative ways to generate these series and make them more realistic by adding the appropriate noise to your given series data. After you complete your first part of this exercise, we are going to use the Scikit-learn regression method to create a machine learning model which learn the sequence based on given series and generate the n numbers by using the regression model. And that is covered in second Jupyter notebook, where a series is given something like this, and here we are using the cosine or cos series, and then using the Scikit-learn regression model here, we are generating the model. And finally, we are generating the 100 more new numbers which are based on our regression model. And at last, we validate that the new numbers which are generated based on regression model are correct and they do lie in the same sequence like others or the source numbers. So we not only generate, we also make sure, validate them and check for their correctness to understand that the mathematical model which we have created using Scikit-learn is correct and it's solving our problem. So let's get started with the first part of our exercise. So we are importing NumPy and Pandas to perform the various numbers manipulation, and Matplotlib is for plotting our x and y values. We are going to start with total number of n 100, means 100 uniform numbers generated using np.random.uniform method. So uniform method helps us to generate random numbers based on whatever the size you would want, 100 between 0 and 1. So that was our x, and initially to start with our y is also equals to x. It could be any function, but if it could be any function, then let's start with basic, just x. So x and y, they both are same. We could see that both x and y's, they are same, and our value of our y is an array of arrays. So now we have 100x and 100y. So our next step going to be to generate the plot. So let's generate the plot. For that we are going to use the plot Matplotlib and the scattered plot, and in the x-axis all the value of x, in the y-axis all the value of y. Here we are using a method called yRavel, and what this Ravel method does is that it takes your multi-dimensional array and it flattened all those values into a contiguous flattened array single. First, see, your y is an array of array, which is definitely a multi-dimensional array. So y.ravel function takes all those values and put them into one contiguous array. So for that reason, we are using here yRavel. This line is just to set up our plotting library. So we could get a wider plot. Height will be the 5 and the width will be the 15 here. And plot is going to look like this for x and y. X is between 0 to 1, y is between 0 to 1, which is definitely certain because of our equation. Now if you would want to change our equation, we could say x square. For the x square, our plot is this way. If you would want to say x square, you can also say np.square and pass x, and let's plot it, which will be the same. If you would say x square and you would want to say you want to have this times x square, so that's why you are seeing more sharpness in your curve. If you would say x square plus x square, you will not see that much sharpness. You could actually call the square root, plot it, that is your square root. Y could be any series which is based on x. Our next step is to learn how to add the noise in our data. So as you see here, this is our x. We generate the random uniform numbers here. And what this noise is, so noise is something which we could add to the x. If we try to add a constant value, for example, here in this example, if we say plus 10, that's going to add everywhere. It will not do any change to us. So let me just make it constant 10. It doesn't do anything to us. So this will not work. We need to have a noise function which changes based on x. That's what we want to apply using our noise method here. So noise is equal to a normal distribution of the numbers between 0 to 0.1 based on size x dot shape. So the total, whatever the shape of x is. So we got x and then noise, and then we are adding noise to our y. And y is equal to, it could be any function. So now we have added that. Let's plot it. This is noise adding a little more disturbance to our series, which is much more realistic. If we would take this noise value and try to make it 0.1, you could see that because of noise is really higher value, because 0 to 0.1 is more higher than 0 to 0.01. So that's why you see that noise is also here adding up to 1.2, So it is not very uniform. It can be uniform if we try to add these numbers. It means what we could do, we could say n equals to 1000. Then it gives you little more resolution what you are expecting here. However, depending on your series, you could choose what is the best option for you to add the noise, and then this way you are much better off if you will not use noise here. For example, you could see that your plot looks like this way, a very straight line, but adding with a little more noise, you are adding more character to your series. One more thing I wanted to explain you is that whatever we are doing here, it would be better if we would convert our operation to two separate functions. One to generate our number series, and second to plot functions. We do not need to copy and paste because we are going to follow various of these mathematical functions. So in the next step, I'm just creating a very simple function where you need to pass n, how many values you would want to generate, and you would want to add noise or not. If you say noise is true, then the noise will be added into x and y. Otherwise not. It's the same thing what we have done, and then within the function you can define whatever your y equals to function will be. And then this is a plot method where we need to pass x and y, and it just generate the plot. Rest, they both you have already covered. So here we are calling the function, we are generating the 100 numbers, true means with noise, and here we are plotting. So if we say noise is false, this is our line. If we say noise is true, now we have noise here. So the next step for us will be to actually create a plot where we could actually see side by side noise and without noise. So before we try to build those plots side by side, we just need to look one more thing, and that is the use of exponential values. So whether we could use np.random.uniform or whether we use np.random.exponential, while the results are going to be similar, however, there are some very big differences. So let's use first where we are using uniform, and our method here is x square plus x plus 1 plus x plus 1. This is our method here is. And our noise is between 0 to 0.1. Let's plot it. And these are 1000 values. And this is uniform. If we do not use the noise here, your equation is like that. Now what we do, we use the exponential value here. Let's use 100 numbers. As you could see that as we grow further and further, there is a big difference in the tail area. Now we use 1000 numbers. So when you are using the exponential distribution of your random numbers, you are going to see a lot more clutter, a lot more closeness as a start, and as you grow further and further, you are going to see a lot more distance between the numbers because of the way the numbers are generated exponential. So for that reason, we want to create a series where we want to have all these numbers uniform. So that's the reason we are using uniform. However, there could be an example or a use case where you would want to use the exponential. So now I have created this side-by-side plots function. What it does, it takes the title and it takes the x1, y1 and x2, y2, and the left side, it creates the x1, y1 based data graph, and right side it creates the x2, y2. So whatever you send left side noise, right side not noise, whatever you will pass, it will generate the graph. So we have defined this method. Now we are just creating this function, new function, which generates the x square, and you are passing how many numbers you would want. So we are passing 100 number with noise is false. We are passing 100 numbers with noise is true, and values are x1, y1, x2, y2. And here is our graph. So this is the series between x and y where noise is not added. Here noise is added. So if we would want to have little more proximity, more better, we can say 0.01, and we are going to get a much better graph. Here our equation is x square plus x plus 1, that is defined here. So let's see how it look like. We have already seen it. Now what if we would want to negative everything. So now it is a negative x square, negative x, negative 1. Let's use this. Make sure y is defined correctly. Yes, and here is our graph. And now your graph is totally upside down. So after this, we are going to generate the graph for x square. So here is x square. Let's build the graph. Here is our x square. And now if we'd say x square minus x. And just using x square minus x, now you can see that we have values on both sides. So even if you use x square minus, and if we try to add a constant like maybe minus 1 here, it's not going to change the curve, because that thing could become a constant. So even if we say this is minus x and this could be plus 1, everything in parentheses, still everything is same. So that's what it says, x square minus x plus 1, and it's really going to look like x square minus x plus a constant. Here we have another example where we are using negative x square plus constant. And that's going to upside down, but very similar because of negative x square. Now our next step is to look into the exponential function. And here y is equal to np dot exponential. So whatever the series of x we are using, we are generating y, which is equals to exponential of x. And here is our series in both cases. As you could see here, the random noise we are adding with between 0 to 1000. And reason we are using this noise, because our series. So what we could do, left side, we do not have the noise. And as you could see here, our distribution is between 0 to 20,000. So if you will use noise 0 to 1, that is not going to work, because y plus noise is not going to create any disturbance if you use series 0 to 1. Even if you use 0 to 100, that is not going to make any changes. Your series is almost going to look identical. So in order to generate the noise which is significant and impactful, you have to add at least 1000, and then that's where if you use 1000 and if you generate your series now it is much more looking practical. So after exponential, next is our logarithmic function. So y is equal to np dot log. So this is just log x, and here we will generate the series, and here is the plot. So the plot values are between negative 0.5 to positive 2.5. That's the reason the random noise is added between 0 to 0.1 range. So after we have covered mathematical quadratic, exponential, logarithmic, next is our trigonometric, where we are going to cover sine, cos and tan. So y is equal to np dot sine, and we are passing x, but we are not passing x. We are passing the x as a constant, which is 2 pi x. And that's what we are using. And then the value of pi is the np dot pi is going to return as 3.14. So let's plot the sine first. And that is our sine value. And then in order to generate the noise, based on this given series, we are adding 0.01. So y is equal to np dot sine 2 pi x. Similar to that, everything is same, only difference is the np dot cos, and here is your cosine or cos function. This is your cos, this is your noise with noise, and finally it is np dot arctan, and exactly 2 pi x, and here is the series which is based on sine, cos and tan. This first part is completed. Now we are going to work on the second part of our exercise. So we are importing NumPy, Pandas and Matplotlib. First method, we are using x square plus x plus 1 with the noise. So x and y, they both are same size. I just wanted to show you that how you could make sure it's correct. Next, we are plotting. So these are our plot. So this is our x and y we have generated, and our method is y equals to x square plus x plus 1. Now what I will be showing you is that how you are going to work in real life scenario. Most of the time when you are working on a problem like that, you might be given a large table where you are going to work with it, your data set or data frame here. So you need to extract the values out from your data frame. So first I will take whatever x and y values we have, I will generate a data frame, and then from using the data frame I will extract the values of x, y, whatever, so that we could perform the machine learning. So here all values is an empty array, and I'm passing the x and y and then creating the all values array. So let's start with, and here make sure this is the xi of 0. Remember, the x and y, they both are multi-dimensional array. So that's why using the I as iterator, we are getting the 0th value, means the very first indexed value. And I have already shown you earlier. So our all values looks like this way. So we have index, value of x, and the value of y. Based on that, now we could create the data frame. So all values, we have 3 columns. So first column is the serial number, second column is the value of x, and the third column is the value of y. So this is our data frame. So now we have a data frame. That is what your real world scenario going to look like. It means if you are given a data frame which is called the df full, where you have this value of x, now you need to predict the 100 more value similar to this function, because even if you choose y or whether you choose x, they both are going to be used the same method here, because y is equal to function of x. So in this example, we are going to use x and this serial number. I will be using one of the given method here. What we are taking is that we are taking this data frame, extracting all the value of x, converting them to a NumPy array. So y is our NumPy array. This NumPy array, if you have NumPy array, we are reshaping into this to -1 to 1, and then if you look into what y became your array of array. That is where you started everything. So if you are not using data frame, you really don't need to convert, because this y is exactly the way you have created earlier. So our y is going to be used here in the machine learning term. Y is the training value which we are training on it, and inside the y, the value of x. Keep in mind, inside the y, the value of x, but variable y here we are going to use subsequently in our machine learning. What is x here? X is the ID. It means this number 0 to 99 is our x ID. So we need to extract x same way. So x, we are taking the x list and we are appending the index here. So you see here, this is just x list is nothing but just an index. So you could actually create index by yourself, but I have shown you in this way. So this is an array of array. So all the value of x list is an array of array, very similar to our y. That's our x list. Now we are taking this x list, converting it to the array and reshaping it. This is pretty much going to look like array of arrays. Now we have x and we have y, lowercase y. Now we are going to add 100 more empty indexes to it, because our objective is to generate 100 more numbers. So we are adding 100 more numbers from 100 to 199. So this is just a sequence, and there could be several ways you could do it. And here is a toPredict array, which is an array of array, but it's not a NumPy array. It's just an array of array, all the values toPredict x. So we are taking this toPredict x, converting it to NumPy array, and then reshaping it to -1 to 1. So we can get toPredict x. After that, let's see what it's going to look like. So toPredict x is an array of array, exactly the same where our x and y, our uppercase x and lowercase y was looking like. Until now, you are okay, because now you have predicted values, which is an array, and then we also have the x and y. At this point, we are going to import this linear regression method from Scikit-learn, and regressor is our object, which is based on this function. Now regressor, we are going to perform the machine learning fit, and that will generate our model, and we are passing x means ID, y means all the x values. One more time, y is your all the x values. So make sure you get that in. Regressor passing x and y. Once model is ready, now using the regressor, we are going to predict. So now we are sending 100 empty index. So this should be able to generate 100 new values, and that will be called the predicted y. So predicted y is our result right now. So based on regressor, we could figure it out what is our m and what is our c. So m is the slope, which is this, and the c right now here, the c is const. Okay, so what happens is that whenever we are trying to generate a sequence of number, that is always going to come up as a mx plus c, where m is the slope, y is the intercept. So once you get that value, based on that, you could predict the next any values. So here I'm creating this new array, which is based on mx, and the value of x is a predicted, whatever the value is predicted, and it's generated the y for us. And again, you see this new y, we are reshaping it, and then once we reshape it, we are just plotting it. So based on that, the value is a straight line. It shows that all the value which we have just generated, they are a straight line here. And then based on value, because the x value here is just a index. So index and the value of y. So that's pretty much is the mx plus c straight line you are always going to get in that scenario. So if you would want to see where all the predicted values are, you could actually see the predicted value. Here are the predicted values based on the mathematical function mx plus c. So let's take a look into the df full. So here df full x, so these are the just value, all the values of x we had. So we can take this value, convert into NP array. So this is what NP array x is going to look like. And if we look into the predicted y is an array of array. So you see here predicted y is an array of array and NumPy array, versus your x values are the array. So reason I'm showing you is that because now what our objective is we need to take the value of x and the predicted value, predicted y, and concatenate them. So now we are going to have total 200 values. So first 100 values are the one which are generated based on our initial function, and then the bottom 100 value we are going to append, they are the predicted value. So for that reason, we need to make sure we have an array where the uniform, both values are in uniform format, so we could concatenate them. So in order to perform the concatenation, we are creating a final y empty array, and all these predicted y values we are appending in the final y here. So predicted y, I, and this is a multi-dimensional array. So now your final y is an array of all the values, which is similar to this, but this is not the NumPy array. This is just, that was an array, and this is the df full x is a NumPy array. So final y, so now final x will be that we will take final y and we will take this df full array and we will try to concatenate them. So let's perform the concatenation. Now our final x is all the values. If we look into the final x, this is 200. So it means that first 100 values are original and next 100 values are predicted. So now we have new x, like the total 200 values. So let's look into whatever our equation was at the very top. So this was our equation. So I'm going to use the same equation, x squared plus x plus 1. So let's use y equals here, and noise, we may not use noise anything. Let me see if we had a noise here. The noise was there, and 0.0.1. So use the same way. So we are using noise here, 0.0.1. Okay. So passing the x, and that's going to generate ours, and x is basically the final x, whatever this one. So it's just uniform x and y, and now let's plot it. So here is your x and y, and if we try to reduce this to 0.01, and this is your sequence really look like. And it look like the new numbers which are also added, but they are somewhere here because that's where the glob is kind of created. If you look into the original set, the original distribution was that between 1, 2, 3, and this is was the original graph look like without any new 100 numbers. And here we have next 100 numbers, but the graph is here. So if you would want to create a new plot which actually shows where these new numbers are, like we can change the color, and once we change the color we can actually see the where the new numbers exist in this new graph. So I already have this function. So based on x and y, they both are identical in terms of total number of values, and here we are using I as an index, x value, y value, and color. Color, first we are using color code 0 and color code 1 after 100 to 199, and 0 to 99 we are using color code 0. So this is our all values, and if we look into our all values, this is just a sequence, index, x, y, and the color code. Then we are converting this to data frame, and first column is a serial sequence number, x, y, and the color code. So that is our data frame. Now we are using data frame to render our graph rather than passing x and y. So it's a similar model where we are plotting this, and just df final x, this df final y, ravel, and c is color. Color is equal to use the color code coming out from df final color. This is the area where the predicted values are visible here. So for equation in our case was x square plus x plus 1, we predicted 100 new values and they are visible here, and it looks like that they are definitely part of the same equation what we have done. Now if you would want to take this equation and convert that to a sine curve. So if we look into what was our sine curve, of the value of function for sine was this. So we take this method, come here and change, only thing we just need to change the y here. So we could say y equals to np sine here, and we are not using any noise, but if you would want we could actually say noise too. Let's use the noise. This is not our y. I will start again this thing. So start everything. Okay. This is our sine curve. So we need to change here. So y is equals to this. Let me remove this. X and y here, and looks like the numbers are generated here in this area, but we already have our method to plot colorful, and let's see, there you go. So these are the areas where we have seen where the predicted numbers are generated. Similar to sine, you could actually try with cosine or cos. So I will use here cos and arctan. So we can come back to top. We could actually say y is equal to cos and this, that's it. Now let's run this very quickly. For the cos, the numbers are generated here. Check here. So you have seen various different mathematical functions, and we made sure that our regression method does generate the values which are correct depending on our source function. If you would want to generate 1000 values, you can also generate them just by changing the method here. Right now we are generating 100, but you can generate even 1000. So before we complete our tutorial, let's move these two Jupyter notebooks from my Google Colab to this Python project's GitHub repo in this predict number series folder, and that is going to go into Python project's repo. So both the Jupyter notebooks are available in this repo. Before we go, let's spend few seconds to complete the recap. So we started our exercise by following various mathematical functions to generate the number sequence. After that, we use that sequence example to learn the pattern using the scikit-learn regression method. Once again, you are not limited to scikit-learn regression. You can use other Python libraries which support regression, and based on regression model, we were able to generate a next sequence of numbers, and then we use plotting library to make sure these new numbers are part of the same series, and we validated that the new numbers which are generated using our regression model are also part of the same original series. So we have also validated our results. So that's all we had to cover in this exercise. I hope you have enjoyed the content. If you like my content, please subscribe it and share with others. Once again, thank you so much for your time, and I'm going to look forward to see you in my next video.